All right, let's take a look at another max-min saddle point problem. So here we have this surface, g of xy equals 1 minus cosine x plus y squared over 2. And we want to see if this has any max-mins or saddle points. So let's try to jump into this without looking at the graph first. So what we want to do first is find our critical points. So you might want to pause the video and see if you can find the critical points on your own, and then start it up when you're ready to go. All right, so to find our critical points, we need to find our partials. So the partial of g with respect to x is going to be, looks like positive sine x. And then the partial of g with respect to y, let's see, we've got 0, 0, and then whatever the derivative of this is, bring the 2 down, cancel it. What is that? Just y? All right, so now to be a critical point, these either have to be undefined or both equal to 0, and there's no value of x for which this is undefined, and there's no value of y for which that is undefined, so now we're just going to try to see where they're both equal to 0. Okay, so set them both equal to 0. This is just a function of x. This is just a function of y, so I don't really need to think about substituting or systems of equations or anything like that. We just solve them individually. So that one's done, right? What about this one? When is the sine of x equal to 0? Now, x is the input value here. It's the input value in this function. We could think about what's the domain of this function. What are the possible values of x? What are the possible values of x here? That's the only issue. Well, I can put anything I want in there, right? The domain of cosine is anything, any angle. It's not being restricted in this case to like between 0 and 2 pi or something like that. So I need to solve this equation for x, thinking that x could be any real number. So when is sine equal to 0? Well, it's equal to 0 a lot, isn't it? Let's see, sine is equal to 0 when y is equal to 0, so that would be at 0 degrees, pi degrees, or yeah, radians, sorry, 0 radians, pi radians, 2 pi radians, etc., and then also negative pi radians, negative 2 pi radians, etc. So therefore there are infinitely many places where x can be make this partial come out to be 0. What does this mean about our critical points? Uh-oh. Is this possibly saying that I have infinitely many critical points? That sounds ominous. That is the case, ladies and gents, and all folks of all ages. So our critical points, we could think about this business here. We could think about a nicer way to write this as saying multiples of pi. So we could say like k pi. X could be k pi, where k is an element of the integers. So remember, the integers are the values -3, -2, -1, 0, 1, 2, etc. And the symbol for integers is a double-staffed z. So actually, the most concise way to write this is to say k is an element of z. Okay, so now we have to analyze infinitely many critical points. Sound fun? So our critical points are k, pi, comma, 0, where k is some integer. All right, let's jump in and see what happens. So let's go ahead and come up with an equation for our second derivative test. And instead of plugging in values, since we have infinitely many values to consider here, let's just write a formula for this. Okay, so let's see. What is the second partial xx? So I need to take the derivative of, where are you? This guy with respect to x. Well, that's pretty easy. That's cosine x times, okay, the partial y. So the partial of this with respect to y, all right, that's pretty easy. That's just 1. So I can take my x partial and then take the derivative with respect to y. So if I do my x partial with respect to y, that's going to be 0. If I did my y partial with respect to x, if I did this, y partial with respect to x, that's just going to be 0. All right, so the second derivative test function that we need to look at is basically the cosine of x. And remember, all we care about is whether this is positive or negative. So let's write our critical points. Let's write them right here, the ones we need to look at, critical points. Maybe let's list out a few of these guys, these k pi zeros, and think about what's happening. So we've got, infinitely many critical points, but maybe we write like negative 2 pi 0, negative pi 0, 0, 0, pi 0, 2 pi 0, right? And just kind of, and then dot, dot, dot. So determining whether this is positive or negative, d of, let me do this. Let's call these our points. Like these are our points. I don't want to write this whole thing. I'll just say d. Is that cool? For this point, this d value is the cosine of x. So it's the cosine of negative 2 pi. All right, what's that? That's just 1, right? That's all the way around. That's just 1. Okay, so that's positive. All right, what about negative pi? What's my d value here? So it's just the cosine of, I better write this down in case I'm losing somebody. So for the point negative pi 0, d of negative pi 0 is just the cosine of negative pi. That's all I need to do is look at that x value. So what, that's 180, so that'd be negative 1, right? So that's negative 1, so that's less than 0. Okay, how about 0, 0? What's my d value? So d of 0, 0 is simply the cosine of 0. Well, that's 1. Can you see where this is going here? That's positive. Okay, how about d of pi 0? Well, that's just the cosine of pi, so we're back to negative 1 again. So that's negative. Okay, so you can see what's happening here. We could keep going. Now, how do I have a set of these that are positive and a set of these that are negative. Now, how could I distinguish what's happening? Let's highlight the positive ones. Okay, that's greater than 0. That one's greater than 0. That one would come out to be greater than 0. Okay, so what can we say about all these that are greater than 0, all these critical points, versus the ones that are less than 0? Yeah, they're all the ones where the k value is even. Okay, so let's consider critical points in the form k pi 0, where k is an even integer. Even integer. So that's all of these yellow ones. Those are all the even integers. Okay, so for those values, we have d of xy coming out to be positive. Okay, now we have to look at, if d of xy is positive, then we have to look at the second partial xx and see what's happening with that. So let's go check that out. So the second partial xx is the cosine of x. That's this piece. I might have it. No, it's just right here. So that's the cosine of x. So for all of these critical points, the cosine of x is 1. So that's positive as well. All right, so for these critical points, the second xx partial is positive as well. So what does that tell us? If they're both positive, we have local minimums. So we have infinitely many local minimums. Holy mackerel, that's exciting. Okay, so all these are local minimums. We have infinitely many local minimums. I bet you're dying to look at the graph. Let's go check it out. All right, here we go. Here's our graph. Kind of neat. Almost looks like a corrugated kind of thing. And I'd encourage you to go graph it for yourself so you can move it around. how you like. So the minimum points are down here. I just put a couple of them in. All right, so we have infinitely many minimum points. If I scroll out, we get more of these bump things. They just go forever. Okay, I just scrolled in so we could see it. Okay, let's go check out those other critical points and see what's happening there. So we have some other infinite critical points where this d value for the second derivative test comes out to be negative. These guys. Okay, so for those guys, we have an odd value, right? Let's make this a little bit bigger. So we have odd values of k. So the next one, like if we did 3 pi, if we did 3 pi 0, my d value would come out to be -1, which would be less than 0. So if I pick an odd value of k, then my d value is negative. Okay, so let's write that down here. Let's pick a different color. So let's consider the critical points in the form k pi comma 0, where k is an odd integer. So for any of those critical points, this d value is coming out to be -1, which is less than 0. So let's go see what that tells us. I think we only have one option there. If that's less than 0, then we have saddle points. We don't have to check anything else. Well, that's good. We have less work to do. So that tells us that, so these are saddle points. Infinitely many saddle points. Let's go take a look at that graph again and see if we can find those saddle points. All right, so I graphed a couple of them here. I've got pi 0, and then I plugged those into the function and got 2 for the output. Let's turn these off. I made them red. And then negative pi 0, I plugged that in. I got 2, -3 pi 0, and 3 pi 0. So we can see those little guys are in here. It's kind of cool. So inside this function, inside these little, oops, I just moved F. Edit, undo. I didn't know you could do that. Well, I just learned something. I grabbed this point and I moved it. Whoa. And then it changed the coordinates. I did not know we could do that. There you go. Discovery. Inadvertent discovery. So the saddle points are occurring inside here, and there's infinitely many of those. Pretty neat. So that's a kind of a cool example. Definitely different, where you have infinitely many critical points.